Today we will be demonstrating how the Knuth-Morris-Pratt algorithm for string matching works. String matching is the process of finding the occurrences of a string, more generally called a pattern, in a text. This is also known as the needle and the haystack problem. Much research goes into optimizing solutions for such a problem, as many fields of study rely greatly on them. String matching is used heavily in the field of bioinformatics. Our DNA can be up to 3 million units long, and we would need to utilize an efficient string matching algorithm to identify certain gene patterns. Another example you are all familiar with is looking for certain phrases in your code while using your favorite text editor. The naive approach to this problem is to use brute force. To do this, we align our pattern to every possible fit in our text, and check whether we find our pattern at that position. For this example, we will use DNA as our alphabet, which is comprised of 4 letters, A, C, G, and T.
Now we will demonstrate an example of the naive approach. This is the text that we use, and this is the pattern. To start off, we compare the first character in our pattern to the first character in our text. We find that it matches. We proceed to compare the next letter in the pattern to the next letter in the text. We discover it matches, so we continue by checking the next character. We come across a mismatch. What do we do next? Upon finding a mismatch, we shift our pattern to the right by 1. We now compare the first character in the pattern to the second of the text. We find a mismatch. We shift again. Oh no, we find another mismatch. Like last time, we shift again. We find that the first character matches, and we'll see that every subsequent character in the pattern also matches to the text. Now that we've found an occurrence of our pattern, we return the position of the first letter of the pattern in the text. If our text was longer, we could continue matching to find every other occurrence. The complexity of a string matching algorithm is usually determined by the number of comparisons we make. For the naive approach, it may be the case that all the characters in the pattern are compared to every character in the text. This would equate to a big O of n times m, where n is the length of the text and m is the length of the pattern. Can we do better?
We will now look at the KMP algorithm, which is similar to the naive approach, but uses some generated information about the pattern to skip some comparisons that are unnecessary. This pre-generated information is in the form of a prefix table. We will demonstrate the generation of this later, so don't worry too much about it now. Here is our prefix table for the example we will be going through. The values indicate how many skips we can make when coming across a mismatch. This will be explained precisely in the following example. This is our example pattern and text. We start by comparing the first character of the pattern to the first of the text. We find that it matches and continue to compare the second character of the pattern to the second of the text. We also find that these characters match, as do the third characters. But the fourth character mismatches. So we now look up the value in the prefix table at that point. We find the value 2. This means we should shift the pattern so that the second index in the pattern is aligned with the mismatched position. This equates to shifting the pattern right by 2. We now compare the index in the text to the new index in the pattern. We find another mismatch, and so we look up the value in the prefix table. We find that the value is 0. This indicates that there are no skips we can make, and so we continue by shifting the pattern right by 1. We now compare the first character of the pattern to where we found the mismatch in the text. Another mismatch. We proceed by checking the value in the prefix table. The value for the first character is always 0, so we shift right by 1. We find another mismatch. The value in our prefix table at that point is 0, so we shift our pattern right by 1. We find a match, and so we proceed to the next character. We find that our second character also matches. The third character mismatches, and so we need to look up the prefix value. We obtain a prefix value of 1. We shift our pattern right so that the first character in the pattern is aligned to the previous mismatch position in the text. This results in shifting our pattern right by 2. We find another mismatch, so we have to shift to the right once again. We find our first character matches. The second character also matches, and so does the third. It is also the case that every other character in our pattern matches. After matching the final character in the pattern, we have found a match. We either return the index at which the pattern appears in the text, or store the index and continue searching.
So that was the general idea of how KMP works. We will now go through how the prefix table is generated. First, some definitions. A proper prefix is a prefix of a string that doesn't include itself. Furthermore, a proper suffix is a suffix of a string that doesn't include itself. So the values in our prefix table refer to the longest proper prefix that matches a proper suffix, up to the end of the subpattern. This might sound quite confusing right now, however we are about to go over an example of generating a prefix table, which should clear it up. We shall be using the same pattern from the previous example. We start by initializing our prefix table to be the same size as the pattern. We start by looking at the first character. There aren't any proper prefixes or suffixes for a string of length 1, so the value is always 0. At the second character, the only possible prefix is A, and the only suffix is C. These do not match, so the value here is also 0. For the third character, we generate the possible prefixes and suffixes up to this character. We can see that the only possible prefixes are A and AC, and the only possible suffixes are A and CA. A is the only prefix that is also a suffix, and it is of length 1. Therefore 1 is our prefix value at this position. Moving forward, we will look at the string up to the fourth character. We notice that the only possible prefixes are A, AC and ACA, and the only possible suffixes are C, AC and CAC. The intersection of these two sets gives us a single string AC, which has length 2. This is our prefix value. The fifth character is an exercise for you. Pause the video now and try to calculate the prefix value. I'm sure you found that easy. We will now go through the answer. The prefixes are A, AC, ACA and ACAC. The suffixes are A, CA, ACA and CACA. We find that there are two matching strings, A and ACA. The prefix generation algorithm is designed to use the longest string, as this will give us the most skips. So we choose ACA, which has a length of 3. So this is the value we assign to the fifth element in the prefix table. Now, exactly like before, we calculate the value for character 6 by considering the substring preceding it. Here is our prefixes and suffixes. As you can see, there are no common elements, therefore we assign the value 0. Like the previous example, there are no common elements in the prefixes and suffixes, so we also assign a value of 0. This concludes our prefix table generation. This precomputation happens before the string matching occurs.
Now we will show you the pseudocode for generating the prefix table. Here is the pseudocode, but firstly we shall go through some variable definitions. The pattern length is denoted by P. The longest prefix that has been found in the pattern is denoted by I. But in this case, prefix actually means the prefix that is also a suffix at the jth index in our pattern P. This will be referred to as our longest prefix hereafter. J is the current index of the pattern for which we are calculating the prefix value for. The prefix table is denoted by the letter pi. Now we will generate the prefix table for the string ATAG using the pseudocode. M is the pattern length, which is equal to 4. The first value in our prefix table is always 0, as explained earlier in our previous example. I is the longest prefix we've found. As we have not found any prefixes yet, it is 0. J is the current index of the pattern for which we are calculating the prefix value. We have calculated the first, therefore we shall calculate the second now. As I is equal to 0, we shall skip the while loop for now. We check if A is equal to T, which is false. We add our longest prefix, I, to the prefix table at index j. We increment j by 1. We check if A is equal to A, which is true. We increment I by 1. We add our longest prefix to our prefix table at j. We increment j to 4. We check if I is greater than 0, and the letter after I is not equal to the jth character, which is true. So we make our current prefix equal to our previously generated prefix value. We check if A is equal to G, which is not true. We add I to our prefix table. The loop terminates because we've reached the end of our pattern, therefore we return the prefix table.
Now, the KMP pseudocode. KMP pseudocode is almost identical to the prefix table's pseudocode. The main difference is the for loop runs for the length of the text rather than the pattern, where the length of the text is denoted by n. The comparisons are now performed against the text rather than the pattern. It performs an extra if that checks whether the longest match is equal to the pattern length or not, to see if it has found the pattern or not. If true, it outputs the result as the first character of the pattern found in the text. Otherwise, the algorithm loops to find all occurrences until the end of the text is reached. So what happens when we don't have any repeating subpatterns? All the values in our prefix table will be 0, and so we will never skip any comparisons. This means KMP will perform exactly the same as the naive method. This is the worst case for any KMP. The worst case complexity for KMP is big O of n times m. The best case is O of n plus m, and because n is usually significantly greater than m, we can say that the complexity is O of n.
The space complexity for KMP is O of m.